So namaskar, adab, sat shri akal, 𝐂𝐤𝐴, 𝐂𝐤𝐴, hello and welcome in GATE Wallah. So student, the subject which we are discussing, vibration for aerospace branch. So in this subject today we are going to discuss new topic, that is forced damped vibration. In last class we have completed free damped vibration of single degree of freedom system. In today class we will discuss forced damped vibration of single degree of freedom vibratory system. Okay. Yes, so starting, first we will discuss the introduction of force vibration. Then we will discuss force vibration of general spring mass system. And during this discussion, we will discuss one more important concept, that is the concept of magnification factor. So these are the topic which we are going to cover today. So without any delay, I am starting. First of all, what is force vibration? So see, in last class we had discussed free vibration, whether it was free undamped or free damped. But what is the meaning of free vibration? If during vibration no external time dependent force or disturbance acts in the direction of vibration, then that vibration was free vibration. So if we are talking about force vibration, definitely what will be its definition? If in the direction of vibration time dependent disturbance or force acts, then that vibration is known as force vibration. Okay, first I am drawing the diagram. Okay, suppose this is a spring mass system. Okay, a spring of stiffness K, and parallel to this a damper is attached. Suppose the damping coefficient of the damper is C. This is the value of point mass. Since damper is attached, so definitely it is damped vibration. But what is the meaning of force vibration? Suppose if we will disturb this mass from mean position by applying a impulse force. Impulse force means we are applying a force for very short duration. And after disturbing this mass from mean position, if we remove the force which we have applied in the mass to disturb it, then it will vibrate like this. But during that vibration, no external time dependent force is acting. Means that vibration is free vibration. But today we are discussing about force vibration. Force vibration means if in this system we are not applying any impulse force, we are applying a force in the direction of vibration which is time dependent. Okay, suppose this is the force which depends upon time. Okay, generally in our syllabus, the force which will apply for disturbance, generally it will be harmonic force. Harmonic force means in the form of sine or cos. Okay, but whatever this force, whether it is harmonic, whether it is exponential, if it is the function of time. So if this force is acting in the direction of vibration, then this vibration is known as force vibration. Just for feeling, suppose in this vibratory system now, instead of right now, suppose this is mean position. Now continuously I am applying a force like this which is varying with time in the direction of vibration. And due to this force, vibration is occurring. So that vibration is known as force vibration. Okay. Now in our syllabus we have to study when this force, external force which we are applying in the direction of vibration is harmonic force. Harmonic force means in the form of sine or cos. Okay. So we will discuss the general case of force vibration, and generally question will come from this general case. In general case, what we are doing, this is a spring of stiffness K. Parallel to this a damper is attached whose damping coefficient is C, and it is connected with the point mass M. Okay, this case we have discussed in free damped vibration also, but now it is forced damped vibration. So in the direction of vibration, external time dependent force will act. That force I am denoting as Ft. Okay, now suppose in our syllabus we have to study that case in which this external time dependent force is harmonic force. Harmonics means it will be in the form of either sine or cos. So suppose this harmonic force is like this, F naught sine omega t plus psi. It will be given in the question. Okay, I am taking in the form of sine, F naught sine omega t plus psi. Even if it is the form of cos, now you can convert that in the form of sine. So ultimately both are discussing in both cases are same. So if you will only focus on this external time dependent force, and if I will ask what is the amplitude of this force, I am not talking about the amplitude of vibration. I am talking about the amplitude of this external force. It is F naught. What is the frequency of this force? Because it is harmonic force, so it will also have some frequency. So frequency of this force means inside sign the coefficient of time, which is omega. So can I say frequency of this force is omega radian per second? That is nothing but forcing frequency. Omega radian per second, which is forcing frequency. Generally, in some time, instead of giving this equation, examiner will give the value of this amplitude of force and this forcing frequency. So forcing frequency is not the frequency of vibration. What is the frequency of vibration? That will come to know after derivation. So what is omega? Omega is this forcing frequency. Okay, psi is phase angle. If required, it will be given. But here, this two value is important, this F0 and this omega. F0 is amplitude of the force applied. And what is omega? Omega is, F0 is amplitude of force. It will be given in the question. And what is omega? Omega is forcing frequency in radian per second. Whenever any data related to frequency is given in the question, be careful whether it is omega, and whether it is omega 2. If examiner is saying forcing frequency, means examiner is talking about this omega. If examiner is saying the time period of force means again forcing time period is given. So that is 2 pi by omega. From that we can calculate omega. But if examiner is giving natural frequency or natural undamped frequency, natural undamped frequency means if in this system free vibration is occurring and no damper is attached, then the frequency of that vibration is natural frequency. And we know for general case the formula to calculate natural frequency, that is omega n, is root k by m. If it is other case, the formula will be root ke by me. But what will be the frequency of this vibration? That will come to know after derivation. So to find the solution for this case, first we will find its governing equation. Okay. Now whatever I am discussing, just try to understand the concept. You need not to mug anything. At last I will make the summary and I will suggest only remember the summary. Okay, see. First we are deriving governing equation. Okay, so to derive the governing equation, I am taking any position in which this mass is disturbed by x distance from in position. Right now I am taking x downward. So see, if x is disturbing by x distance from mean position, so velocity will be x dot, acceleration will be x double dot. Since we are calculating x dot and x double dot by differentiation, so their direction will be same as x. Okay. Now, okay, all the force we will apply in the body of mass. So first force which will come is restoring. We already discussed in this spring mass system, there will be no role of gravity in the restoration. This we already discussed in earlier classes also. Reason? Because the weight of this mass is supported by spring. So definitely can I say here, due to weight of the system, there will be some static deflection in the spring. And since due to weight of the system, there is static deflection in the spring. So what will happen? The weight and the force due to static deflection in the spring will cancel each other effect. How they are cancelling each other effect, we need not to bother about that. But if due to weight there is static deflection in the spring, they will cancel each other effect. And in that case, there will be no role of gravity in the restoration. Means here restoration is occurring only due to stiffness. And if restoration is occurring only due to stiffness, while considering restoration, neither will consider weight nor will consider static deflection of the spring due to weight, because they are cancelling each other effect. But how they are cancelling, don't bother about that. So neither I am considering weight nor I will consider static deflection of the spring. Only I will see what is the deflection of a spring from mean position. We need not to bother about the deflection of spring at mean position due to weight. Okay. So see, right now the displacement of mass from mean position is x and spring is directly connected to the mass. So can I say displacement of spring from mean position will also be x? So here restoring force will be stiffness of the spring K, displacement from mean position is x. So restoring force will be Kx. In the body of mass, it will be opposite to x. Right now x is downward, so it will be upward. Okay. Next, since damper is attached, so we'll apply damping force. So what is the expression of damping force? So see, the damping coefficient of the damper, it is C. Now it's velocity, because for damping force velocity is required. Now damper is directly attached to the mass. So displacement of mass from mean position is x. So can I say displacement of damper also from mean position will be x. And since displacement is x, velocity will be x dot. Okay. So damping force will be C, damping coefficient into velocity, which is x dot. Now it will be opposite to x dot. Right now x dot is downward, so it will be upward. Next, this force is already acting in the system, already applied. But since vibration is occurring, so it is not in equilibrium. So here, if I want to use the equation of equilibrium, I need to apply pseudo or inertia force. So see, this mass is translating, that's why we will apply pseudo force or inertia force. And what will be this expression? So mass of this body is m. Now its acceleration, so its acceleration is x double dot. So pseudo force will be mx double dot, and this direction will be opposite to x double dot. Right now x double dot is downward, so it will be upward. Now after considering this inertia force, now we can use the equation of equilibrium. So can I say in this FBD, summation of force in y direction will be 0 after applying inertia or pseudo force? Yes. Now while using this equation, suppose I am adding upward force, and if we are adding upward, we'll subtract downward. So right now mx double dot is upward, which I am adding, so it will be plus mx double dot. Next, damping force is also upward, which I am adding, so it will be plus cx dot. Then restoring force kx, it is upward, so which I am adding, so plus kx. This force is downward, which I am subtracting, it is minus f naught sine omega t plus psi. This is equal to 0. Okay. Now it will be mx double dot plus cx dot plus kx. Now you can see now this is the function of time only, and here time is independent variable. Here x is dependent variable. See, x dot is dx by dt, x double dot is d square x by dt square. So here x is dependent variable and time is independent variable. So you can see in this equation one separate function of time is coming, that is independent variable is coming. Shift that function in RHS. So this equation will be like this. If plus, this minus will come this side, it will become plus. So plus f naught sine omega t plus psi. Okay. Now you can see now, if we try to recall last class we had discussed free end vibration. And for general case, in free end vibration, LHS part was same. It was mx double dot plus cx dot plus kx. But in free end vibration, RHS was 0. But here, if in the vibration, external time dependent force is x, in that case, in RHS, separate function of time will come. Here, separate function of time is coming. Now here, if you want to find its solution, solution means x as a function of time. So how we can find? See, it is the double order linear differential equation. You can write x double dot as d square x by dt square. Okay, plus x dot as dx by dt plus kx equal to some function of independent variable, which is f naught sine omega t plus psi. Okay. Now it is double order linear differential equation. Why? Because here you can see the power of this dependent variable x is 1. Power of this differential coefficient is also 1. Power of this differential coefficient is also 1. Means it is double order linear differential equation with constant coefficient. Constant coefficient, why? Because here the coefficient of this dependent variable is k, which is a constant. Coefficient of this differential coefficient is c, which is also a constant. Coefficient of this differential coefficient is m, which is also a constant. So this is double order linear differential equation with constant coefficient. And for this case, if you want to find the solution, what is the how we can find? For this, we'll find CF plus PI. Now for CF plus PI calculation, what we do? But here na, I will not go in mathematics too much, because that mathematics is not required na. How to find CF, how to find PI, you will be studying mathematics. Okay, just for understanding, I'm explaining. If you want, what we do now, if you want to find a solution, we replace d by dt by operator capital D. And we replace d square by dt square by operator d square. So it becomes md square plus cd plus k into x, which is equal to f naught sine omega t plus psi. So if by doing this replacement, if we are getting equation like this, some function of operator d into dependent variable, separately some function of independent variable, it can come. So that equation is nothing but it is linear differential equation with constant coefficient. And to find its solution, we'll find CF plus PI. Now what is the difference now? In free end vibration, since RHS was 0, so that's why in that case now PI was 0. But here, since in RHS some independent variable of time is coming now, so here pi will also come. Here pi is not 0. So here we need to find pi also. That is the difference. But what about CF? So can I CF calculation will be same? Because in free end vibration also we were getting this equation in LHS, and here also same equation, and CF depends upon the function of operator D. So since this equation is same as free end vibration, so here whatever solution we got for free end vibration, can I say that is the CF part for force vibration, not solution, CF part. And separately we need to calculate pi. Now if we are assuming zeta is less than 1, if we are talking about CF now, CF will be periodic. I am talking only about PCF. But amplitude of CF will reduce with time. That I discussed in last class. If zeta is less than 1, what was the solution of free end vibration? If you try to recall, it was like this. A e to the power minus zeta omega and t. Only try to understand. Na? Don't memorize anything. At last you will understand everything. Sine omega d t plus phi. Try to recall. Where a and phi was arbitrary constant which will depend upon boundary condition. Omega d was frequency whose formula was omega and root over 1 minus zeta square. But even this expression is valid when zeta is less than 1 in CF part. If zeta equal to 1 or greater than 1, then in this equation no periodic term will come. Okay, you need not to remember those derivation, but no periodic term will come. But this is not the solution in force vibration. Is this CF for force vibration? And even this equation will get when zeta is less than 1. If zeta is equal to 1 or greater than 1, this part will not be periodic. But ultimately you can see whether it is periodic or whether it is not periodic. Right? It is periodic. But in this equation you can see its amplitude will reduce gradually with time. Okay, even when zeta is equal to 1 or greater than 1, in that case also CF will reduce with time, but it will not be periodic function. But here don't go in this equation too much. Here pi is more important. So here what I am trying to say now, if you want to find complete solution, that is equation of x, you need to find pi also. Okay, pi also. So now I am doing calculation for pi. Okay. If exam asks you what is the frequency of force vibration, don't say it is omega d, because it is the frequency of CF part. But for complete solution, we need to calculate pi also. Now pi depends upon this function. What is the method to calculate pi? I will not go in the calculation. But if you want to calculate pi, now we calculate like this. 1 upon function of d, which is this. F0 sine omega t plus psi. Okay, now this derivation you will how to calculate pi from this equation, that we will study in pi mathematics. But we are not going in mathematics part. From this if you will calculate pi, whatever final expression will come that I am writing directly, and that you have to remember. But write down, don't remember anything. At last I will make the summary, only remember the summary. So if you will calculate pi for this case you will get this equation. F0 sine omega t plus psi minus theta upon root over k minus m omega square whole square plus c omega whole square. See, here one new term theta is coming. So here I am writing the expression of theta also. Here formula to calculate theta is tan theta is equal to c omega upon k minus m omega square. Okay, I will write pi in two form. We have to remember any one form. That okay. So first I am writing first form. This is the first form. From this equation, if you will calculate pi, you will get like this. How you can remember this See, this external time dependent force was simple harmonic So for this force, when we will calculate pi, it will also be simple harmonic with same frequency. So frequency of this force is omega. So you can see frequency of pi is also omega. Okay. Okay. But when we will get some phase difference by behind the theta angle. Behind means minus theta. So it is like this. Since it is simple harmonic, it is a simple harmonic. Simple harmonic means it will have some amplitude first. So amplitude of pi I am denoting as capital X. Only we need to remember this expression. So Pi is also simple harmonic with same amplitude. It is not the amplitude of this, it is the amplitude of Pi, which is capital X sine. It is omega t plus psi. So here it will come omega t plus psi, means frequency same, but along with minus theta will come. In which this is the formula to calculate capital X, and this is the formula to calculate theta. So you can also write like this, na? Write cap like this. Pi will be amplitude is of Pi is suppose capital X sine same frequency omega t plus psi with phase difference theta. Where formula to calculate capital X is f naught. Now it is easy, upon root over k minus m omega square whole square plus c omega whole square. And formula to calculate theta is this. If I will ask what is the amplitude of Pi, that is capital X, whose formula is this. What is the phase difference between this force and Pi? Theta. And this is the formula to calculate theta. Tan theta equal to c omega upon k minus omega m omega square. Okay, this you have to remember. Okay, in force vibration, Pi will be simple harmonic if this force is simple harmonic with same frequency. Only difference is its amplitude is capital X and phase difference is theta. So capital X sine omega t plus psi minus theta is coming, where this is the formula to calculate capital X and this is the formula to calculate theta. Okay. But this expression of capital X and theta, na, I am converting in one more form. Okay. That second form is more important. Okay. For numerical, I will suggest only remember the formula of second form. See, what we are doing now, first I am converting the expression of capital X. I am trying to convert this expression now in terms of zeta. What is zeta? Zeta is damping factor. Okay, because since damper is attached, so to relate any parameter with damping effect, na, generally we represent that parameter with zeta. Second, we are trying to convert this expression in terms of R. What is R? Na? This R is known as frequency ratio. And frequency ratio is nothing but it is the ratio of omega and omega n. What is omega? Sir, omega is forcing frequency, which is the forcing frequency means frequency of force. Now you can tell omega is also frequency of Pi also in radian per second. And what is omega n? Omega n is definitely natural undamped frequency. For general case, we know the formula to calculate omega n is root k by m. Okay. So I am trying to convert this expression in terms of zeta and R if possible. So for that, what we are doing, the expression of capital, only right now understand the concept. At last, I will make the summary. You have to remember only summary. F naught upon root over k minus m omega square whole square plus c omega whole square. Capital X. What I am doing now, from below side, from inside this square root, I am bringing k square common. And if you take k square common and if you bring outside root, can I say it will become k? Because the square root of k square is k. Means from inside root we have taken k square common. So now can I say inside root we need to divide this expression with k square because we have taken k square common. Now if we divide this expression with k square, so here square is also already coming. So divide this term with k. So k by k will be 1 minus it will be m omega square by k. Yes. Plus here square is already coming, so divide this with k, so it will become c omega by k whole square. Okay. Now why I am doing this? You can see here k by m is coming. Now we know omega n is root k by m. So k by m will be omega n square. So if we bring this m below side, it will become k by m. And I can replace k by m by omega n square. And after doing this replacement, it will be omega by omega n whole square. And omega by omega n is r, so it will be r square. So ultimately, if we will do this conversion, f naught k, I am writing below side upon k upon root over, it is becoming 1 minus, sorry, this is square I left. So 1 minus r square, because it is becoming omega n square and omega by omega n is r, so it will become r square whole square plus this c omega by k term is coming. Now whenever we are doing the derivation of force vibration, this term will repeat during derivation again and again. And whenever c omega by k is coming now, c omega by k is nothing but it is 2 zeta. How I'm doing the derivation. See, we already derived the expression of zeta. Expression of zeta is c upon 2 root over km. From this you will find the expression of c, it will be 2 zeta root km. But we had to find c omega by k. So both side I am multiplying omega by k. So it will be c omega by k, that is equal to 2 zeta root km into omega by k. So c omega by k expression is coming. It is 2 zeta. Now see, root k upon k will be, below side root k will come because k by root k is root k. So it will be root m by k into omega. Okay. Now we know root k by m is omega n. So root m by k is 1 by omega n. So it will be 1 by omega n. So ultimately it is coming 2 zeta 1 by omega n into omega means omega by omega n. And omega by omega n is nothing but r. So can I say c omega by k is 2 zeta? You need not to remember this. This is only for derivation. Okay. So we come to know c omega by k is 2 zeta. So I am replacing this with 2 zeta r whole square. So finally, can I say the expression to calculate the amplitude of pi, that is capital X, is f naught by k upon this expression. Okay. What is the benefit of this equation? You can see now, apart from f naught by k, whatever term is coming now, that is a dimensionless number. Is having no unit. Because see, capital X is the amplitude of pi. Its unit definitely it will be either meter or mm. Now you can see the unit of f naught by k is also meter or mm, because it is nothing but force divided by stiffness, and force divided by stiffness represent deflection. So that's why other term is dimensionless number. Yes. So this is the expression of capital X. Similarly, if you try to find the expression of theta now, so we already know tan theta is c omega upon k minus m omega square. Now from below side, if we will take k common, it will become c omega by k upon, from this equation we have taken k common, so divide this with k. So k by k will be 1 minus m omega square by k. Now again c omega by k is 2 zeta upon 1 minus. This term is again r square. Why? Because k by m is omega n square, so it will be omega by omega n whole square, and omega by omega n is r, so it is r square. Okay. So expression of theta is tan theta is also 2 zeta r upon 1 minus square. So whether you are remembering this equation or not, but I will suggest in terms of zeta and r, always remember the equation. Okay, always remember the equation. So now if I will make a final summary, can I say for this force vibration, if external time dependent force is coming, so governing equation was like this: mx double dot plus cx dot plus kx. Because for this equation we have found the solution now. F naught sin omega t plus I, where F naught is the amplitude of force, omega is force frequency. Now for this, if you want to find complete solution, that is x, it will be CF plus PI. Okay. CF expression I am not writing, but it is 100% sure whether in CF equation periodic term is coming or not. If zeta is less than 1, periodic term will come. If zeta equal to 1 or greater than 1, no periodic term will come. This is about CF. I am not talking about complete solution. But it is 100% sure the CF part will reduce with time. Reduce with time. Okay, it is 100% sure. But here I am writing only the expression of Pi right now. CF plus Pi. CF we know, if zeta is less than 1, it will be a to the power minus zeta omega n t sin omega dt plus pi. If zeta equal to 1 greater than 1, it will not be periodic. But ultimately CF will reduce with time. It is 100% sure. But what about Pi? Here Pi is more important. Now, if this external force is simple harmonic, now remember Pi will also be simple harmonic with same frequency. So, suppose the amplitude of Pi I am denoting as capital X, to it will be capital X. Here in force sin omega t plus psi is coming, so it will be capital X sin omega t plus psi minus theta. Suppose this force is F naught cos omega t, so it will be capital X cos omega t minus theta. If it is F naught sin omega t, it will be capital X sin omega t minus theta. If it is F naught sin omega t plus pi by 2, it will be capital X sin omega t plus pi by 2 minus theta. So amplitude of Pi is capital X and theta is phase difference. And the formula to calculate amplitude of Pi, that is capital X, is either F naught upon root over K minus M omega square whole square plus C omega whole square, or in terms of zeta and R, it is F naught by K upon root over 1 minus R square whole square plus 2 zeta R whole square. This is the final summary. And the formula to calculate theta is tan theta is either C omega upon K minus M omega square for general case, or it is 2 zeta R upon 1 minus R square. Whether you are remembering this or not, but I will suggest always remember this equation. So what we'll do in numerical, I will use this. So this equation will automatically get fit in our mind. Okay. So this is, now here I am discussing one interesting result. If we draw the graph of x, now x is CF plus PI. Okay. Now try to understand this CF part. If CF part, it will reduce gradually with time. This is the expression graph of CF. By I am drawing this graph by assuming zeta is less than 1. Even if zeta equal to 1 or greater than 1, CF is not periodic, but it will also reduce with time. So whether zeta is less than 1, zeta is greater than 1 or equal to 1, you can see ultimately CF will reduce with time. So after some time CF term will be negligible, can I say? But x is not CF, x is CF plus PI. Okay. And PI, whether zeta is less than 1, equal to 1, greater than, doesn't matter. PI is always simple harmonic with constant amplitude capital X. And frequency of PI is omega. So we'll draw the graph of PI. Can I say it is simple harmonic with constant amplitude capital X? Now X is CF plus PI. So can I say if I will draw the graph of X, that is CF plus PI, initially due to the presence of CF part, because initially the effect of CF is more, the X, okay, but with time the effect of CF is reducing. So can I say when I will draw the graph of CF plus PI, initially the amplitude will reduce, but after some time the effect of CF will be negligible, and when effect of CF is negligible, then can I say the graph of X will be same as PI, because after some time effect of CF will be negligible. Means what I am trying to say, if you draw the graph of X now, this is important. Initially the amplitude of graph will reduce, but after some time when the effect of CF is negligible, the graph of X will be same as PI. So initially it is reducing, but after some time when the effect of CF is negligible, here we are assuming the effect of CF is negligible. And when effect of CF is negligible, the graph of X is same as the graph of PI. Okay. Now see, definitely whatever vibration is occurring, whether it is zeta is less than 1, equal to 1 or greater than 1, can I say it is in all the cases, if it is force vibration, after some time effect of CF will be negligible. And when effect of CF is negligible now, then that force vibration is known as steady state vibration. Okay, and generally when we are doing the analysis of force vibration now, we do the analysis of force vibration by assuming steady state vibration. Steady state vibration means X is equal to PI, by assuming the effect of CF is negligible. Because in all force vibration case, after some time we already know effect of CF will be negligible. Okay, so generally in force vibration questions comes related to steady state vibration. Steady state vibration means we are assuming CF is negligible. And if CF is negligible, X will be equal to PI. If I will ask what is the amplitude of steady state vibration, X is equal to PI. So amplitude of PI means amplitude of steady state vibration, which is capital X. If I will ask what is the frequency of steady state vibration, it is omega, which is the frequency of PI also. Because we in all force vibration case, we know after some time the effect of CF will be negligible, and when effect of CF is negligible, X will be equal to PI, and that vibration is known as steady state vibration. Means if I am saying steady state vibration, it simply means X is equal to PI, because we are assuming CF negligible. And we know if external time dependent force is simple harmonic, PI is also simple harmonic with amplitude capital X. If force was sine omega t plus psi, it will be sine omega t plus psi minus theta. So this is the equation of Pi and this is the equation of steady state vibration. So if examiner asking what is the amplitude of steady state vibration, so can I say it is the amplitude of Pi, which is capital X, and this amplitude is also known as steady state amplitude. Steady state amplitude means amplitude of steady state vibration. So here capital X is also known as steady state amplitude. Means if examiner is saying calculate the amplitude of steady state vibration, means we have to calculate steady state amplitude, capital X. And formula I am writing in terms of zeta. Our formula to calculate capital X is F naught by K, where F naught is the amplitude of force, K is the stiffness of the spring for general case, upon root over 1 minus R square whole square plus 2 zeta R whole square. We know zeta is damping factor. For general case, formula to calculate zeta is C upon 2 root over Km, and R is frequency ratio, which is omega by omega n. What is omega? Omega is forcing frequency. Can I say omega is frequency of Pi also in radian per second? And omega is also the frequency of steady state vibration. Okay. And omega n is definitely natural undamped frequency. Okay. Okay. Clear? Now, this phase difference, if exam asking the formula to get phase difference, tan theta is 2 zeta R upon 1 minus R square. So that's all about force vibration. If question is coming from general case, exam asking, I will ask calculate the amplitude of steady state vibration. Generally this question comes, or steady state amplitude. So definitely examiner will give the amplitude of force, stiffness of the spring. You can calculate natural frequency, forcing frequency will be given, so you can calculate R. Zeta, either damping factor examiner will give directly, otherwise examiner will give the value of damping coefficient of the damper, so you can calculate zeta also, because formula to calculate zeta is C upon 2 root over Km. You will put here, you will get steady state amplitude. Okay. If exam asking phase difference, this is the formula to calculate phase difference. Okay. Now we'll solve some numerical, but before that now, in force vibration, one more important concept comes, which is the concept of magnification factor. In short, I am writing MF. So first I am defining this MF. Okay, and generally from this MF, numericals comes, but some questions comes related to the graph of MF also, that I will draw, don't worry. So I will discuss that graph also. But what is magnification factor? So see, in force vibration, the expression of steady state amplitude, okay, is F naught by K upon root over 1 minus R square whole square plus 2 zeta R whole square. Okay. Now you can see here now, this apart from this, means if you bring this F naught by K this side, so it is capital X by upon F naught by K. So this term is dimensionless term, 1 upon 1 minus R square whole square plus 2 zeta R whole square. So ultimately this ratio, which is the ratio of capital X and F naught by K, it is the dimensionless ratio, and this ratio is known as magnification factor. So if I will define mathematically what is magnification factor, so simply can I say it is the ratio of steady state amplitude. I am not writing because this equation is self-explanatory. It is the ratio of steady state amplitude, that is capital X, and F naught by K. F naught by K means, can I say, okay, only to define this term, if in a spring whose stiffness is K, if you will apply a static force F naught, the deflection of that spring will be F naught by K. This is only for calculation purpose. Means it is the static deflection of the spring due to force F naught, which is the amplitude of force. Okay. And this ratio is known as magnification factor. And what we want, this ratio should be less or this ratio should be more. I want that this ratio should be as low as possible. For the range in which this ratio is more na, that range is not desirable. Because if ratio will come more, capital X will come more, and more value of capital X is not desirable of the system. Suppose for any system, capital X is coming 2 meter. Means the amplitude of that vibration is 2 meter. Okay, so that much amplitude is not practically possible. What will happen? System will break into two parts. So that's why I don't watch too much capital X, because it is not desirable for system. That's why I don't want too much value of magnification factor. And for the range in which magnification factor is high, that range is not desirable. not desirable. Okay. But for numerical, the form. Now you can remember the equation of both MF and X with this single equation. Because this is MF, exam asking MF, calculate this, exam asking capital X, shift F naught by K this side. Okay. Now here separately I am only writing the expression of MF. It is 1 upon square root of 1 minus R square whole square plus 2 zeta R whole square. Okay. So for numerical this is completed. But from this equation now I am drawing a graph. What I am doing? I am drawing a graph between magnification factor. In y-axis I am taking magnification factor and R is frequency ratio, that is omega by omega n, for any fixed value of zeta. Means I am assuming zeta is constant. Like at one time I will draw the graph for zeta equal to 0. Then I will draw the graph for zeta equal to 0.1, 0.2 like this. Means we are drawing the graph between MF and R for any fixed value of zeta. Because now, what I am trying to say, if you are design the system, means in that system if you attach the spring, you attach the damper, the mass of the system you already know, means the value of zeta will get fixed. The value of omega n will also get fixed. But which type of force I am applying, that force will decide the value of forcing frequency omega. But so sometime na this forcing frequency omega is in our hand. So if I am assuming omega can change. So if omega can change, then R can also change. So actually now for any particular system R is variable. Okay. So R is variable. So that's why I am drawing the graph between MF and R for any fixed value of zeta. And for the range of R for any fixed value of zeta in which MF is coming more, that range is not desirable. Okay. Not the value range of R in which MF is lesser, that range is desirable. But the value of R at which MF is more, or you can say if MF is maximum at any value of R, that is critical value, that is not desirable, that I don't want. Okay. Yes. So I am drawing the graph between MF and R for any fixed value of zeta. Now first I am explaining how you can draw the graph. So don't remember anything, only try to understand. At last now I will make summary related to graph also. Only you need to remember those summary. See, first I am drawing this graph now. Only understand, don't write anything, only understand. For zeta equal to 0, we are drawing the graph for any fixed value of zeta. So first I am taking any one simplest value of zeta, which is 0, means I am assuming no damper is attached. Now if you draw the graph for zeta equal to 0, this equation will be like this: MF equal to 1 upon square root of 1 minus R square whole square. Zeta is 0, so this part will be 0. Okay. Now see, you will see this equation now. Initially, if you increase the R from R equal to 0, if you put R equal to 0 here now, you will get MF equal to 1. If you put R equal to 0 now, you will get MF equal to 1. You can check. By putting R equal to 0, we will get MF equal to 1. Now, initially, from R equal to 0, if you increase the R now, okay, initially MF will increase. Reason? Here, if you put R equal to 1, you can check. If you put R equal to 1, now below side you will get 0, and 1 by 0 is infinite. So can I say at R equal to 0, definitely MF is 1, and at R equal to 1, MF is infinite. So can I say from R equal to 0 to R equal to 1, MF will increase, and at R equal to 1, it will be infinite. That is not desirable, because infinite means system will get collapse. So when I will use practically this system now, I will not use in this range, because that is not desirable. So to find undesirable range, I am drawing this graph now. So okay. So at R equal to 1, MF will infinite. Now MF is infinite, now MF cannot be more than infinite now. So definitely after R equal to 1, if you increase R, MF will decrease. So after that, by increasing R, MF will continuously reduce. Miss, can I say, don't write, only understand. At last I will make the summary. But if you will draw the graph for zeta equal to 0, means when there is no damping, for from R equal to 0 to 1, MF will increase, means MF is maximum at 1, R equal to 1, and its maximum value is infinite. After that, MF is continuously decreasing. Okay. Means if you are drawing the graph on a fixed value of zeta now, what is the method to draw the graph? First, find the value of R at which MF is maximum. And what is the maximum value of that MF? For zeta equal to 0, MF is maximum at R equal to 1 and maximum value of MF is infinite. That's why from R equal to 0 to 1, MF is increasing. At R equal to 1, it is infinite. After that, MF is decreasing. But this is for zeta equal to 0. Now, what will happen if I am drawing the graph for zeta equal to 0.2, zeta equal to 0.3, zeta equal to 0.4? But like this, various value of zeta is possible, na? So, suppose right now the fixed value of zeta I am denoting simply as zeta. Now, I am drawing the graph when the fixed value of zeta is between 0, because for zeta equal to 0, we have drawn the graph, and 1 by root 2. Okay. Why I am drawing the graph for this range, you will understand, don't worry. So now whatever I am going to explain right now, that is only valid when zeta is between 0 to 1 by root 2. Okay. Now see, when I was drawing the graph for zeta equal to 0, I have found at which R MF will be maximum. So I come to know MF will be maximum at R equal to 1. Similarly, if we are drawing the graph for any other value of zeta, again we have to find at which R MF will be maximum. MF is maximum at R equal to. For that, what we'll do now, if you want to find the R at which MF is maximum, for that you need to differentiate this equation with respect to R. With respect to R. By assuming zeta is constant and equate with 0. So you will get the value of R. You will get the value of R. Just 1 second. You will get the value of R at which MF will be maximum. You will get the value of R at which MF will be maximum. So if you will differentiate this equation with respect to R and equate with 0 now, you will get this expression. R equal to root over 1 minus 2 zeta square. At this value of R, MF will be maximum. This equation is valid even for zeta equal to 0. Here, if you put zeta equal to 0, you will get R equal to 1. And we already know for zeta equal to 0, MF was maximum at R equal to 1. Okay. But why I am saying this equation or whatever I am discussing here is valid for this range? Okay. Because now if you put the value of zeta which is greater than 1 by root 2, inside this square root you will get imaginary number. And R can never be imaginary because it is frequency ratio. So that's why if zeta is greater than 1 by root 2, this equation is not practically valid because you will get imaginary number. Okay. So that's why this equation is only valid for zeta between 0 to 1 by root 2. Okay. So for numerical, you can remember like this, but at last I will make the summary. MF is maximum between zeta 0 to 1 by root 2. MF is maximum at R equal to root over 1 minus 2 zeta square. Like suppose if zeta is 0.1, okay, 0.1 is between this range. So examiner asking for zeta equal to 0.1, MF will be maximum at which value of R? Put zeta equal to 0.1 here, you will get the R at which MF will be maximum. Now second question which can come, what is the maximum value of that MF? Like if zeta equal to 0, for zeta equal to 0, maximum value of MF is infinite. But what will be the maximum value of MF for zeta equal to 0.1? So what we'll do, we'll put zeta equal to 0.1 here, we'll get the value of R at which MF is maximum. Okay, and that value of R and zeta equal to 0.1 will give it here, we'll get maximum value of MF. But if we'll put this expression, because we know in this range, MF is maximum at this R. So simply if I will put R equal to root over 1 minus 2 zeta square, means R square equal to 1 minus 2 zeta square in the equation of MF. Can I say I will get the expression of maximum value of MF for that zeta? Okay. And this question is general question because examiner generally ask at which R MF is maximum and what is the max value of MF. So if you want, you can separately remember the expression of maximum value of MF for any zeta. So if you put this expression, I am not going in derivation. If you put R equal to root 1 minus 2 zeta square or R square equal to 1 minus 2 zeta square in the expression of MF, you will get the expression of maximum value of MF for any fixed zeta. Okay, and if you'll do derivation, you'll get this expression 1 upon 2 zeta root over 1 minus zeta square. Yes, you'll get this expression. Okay. If you'll put this equation in the equation of MF, you'll get this equation. So this is the formula to calculate maximum value of MF for any fixed zeta. If you put zeta equal to 0 here, now you'll get 1 minus 0, that is infinite. And we already know for zeta equal to 0, maximum value of MF is infinite. But what if exam asking what is the maximum value of MF for zeta equal to 0.1? 0.1 is for this range. So put zeta equal to 0.1 here, you'll get the maximum value of MF for zeta equal to 0.1. Exam asking what is the maximum value of MF for zeta equal to 0.2? Put here, you will get maximum value of MF for that zeta. But if exam asking what is the maximum value of zeta maximum value of MF for zeta equal to 0.9. So don't be in a hurry. You put 0.9 here, you will get maximum value of MF. No, that is not valid. Because 0.9 is greater than 1 by root 2, so it is not coming in this range. Because whatever I am discussing here, it is only valid for this range. Okay. So for this range, MF will be max at this R, and this is the expression to calculate maximum value of MF. This is for numerical. But what changes will come in the graph? So see, what changes will come in the graph, na? So see, if we will carefully focus on this equation, na, from zeta equal to 0, if we increase the graph from zeta equal to 0 to 1 by root 2, it will increase the zeta, na, the value of R at which MF is maximum. MF is maximum at R equal to root 1 minus 2 zeta square. But in this equation, put zeta equal to 0, you will get R equal to 1. That we already know. For zeta equal to 0, MF is maximum at R equal to 1. Now, in this equation, if you put zeta equal to 1 by root 2, you will get R equal to 0. You can check. Put zeta equal to 1 by root 2 here. 1 by root 2 square will be 1 by 2. 1 by 2 into 2 is 1. 1 minus 1 is 0. Miss, what I am trying to say now, from zeta equal to 0 to 1 by root 2, if we are increasing the zeta, the value of R at which MF is maximum, it will shift towards the left side of R equal to 1. R equal to 1. Because you can see the value of R at which MF is maximum, if you are shifting from zeta 0 to 1 by root 2, it is reducing. Here it is R equal to 1. For zeta equal to 0.1 now, what I am trying to say, the value of R at which MF is maximum, it will be less than 1, but it will be greater than 0. Similarly, for zeta equal to 0.2, what the value of R at which MF is maximum, it will be lesser than this, but it will be greater than 0. At zeta equal to 1 by root 2, MF will be maximum at R equal to 0. Clear? This is first conclusion. Only understand, don't understand this, but this picture will automatically get in your mind when you will draw the graph. Similarly, what about the maximum value of MF? See, at zeta equal to 0, maximum value of MF is infinite, that we already know. Similarly, if we put zeta equal to 1 by root 2, na, the maximum value of MF will come 1. Maximum value of MF will come 1. Okay. If you can check, if you put zeta equal to 1 by root 2, maximum value of MF will come 1. Okay. Now, but what will be, what maximum value of MF for zeta equal to 0.1 na? For zeta equal to 0.1, whatever maximum value of MF will come na, it will be less than infinite. MF maximum value, it will be less than infinite, but it will be greater than 1. Similarly, what about zeta equal to 0.2? Whatever maximum value of MF will become, it will be lesser than this value, but it will be greater than 1. What I am trying to say, if you are zeta is changing from 0 to 1 by root 2 na, the value of MF max will reduce. Okay. Now I am showing these things in the graph. It will be better clear. Suppose I am drawing the graph for zeta equal to 0.1. See, whatever is the value of zeta na, for all zeta at R equal to 0, MF will always be 1. So always start the graph from this point. Because na, see, in this equation, if you put R equal to 0, this part R equal to 0, it will be 0. So 1 minus 0 whole square means 1 square. And if r equal to 0, this part will be 0. So below side root 1 will come. Root 1 is 1 and 1 upon 1 is 1. So for all zeta, the value of MF at r equal to 0 will be 1. So always start the graph from this point. Now, suppose I am drawing the graph for zeta equal to 0.1. What changes will come in the graph? Okay. So first of all, the value of r at which MF is maximum will shift towards the left side of r equal to 1. So suppose we are getting MF maximum somewhere here. Okay. Now what about the maximum value of MF? That will be less than infinite but greater than 1. So suppose it is coming somewhere here. Like this. Okay. Now if you want to do exact calculation that at which RMF is maximum, so put zeta equal to 0.1 here. What is the exact value of MM maximum? Put zeta equal to 0.1 here. But whatever it will come, value of R at which MF is maximum will be less than 1 and value of MF maximum will be less than infinite but it will be greater than 1. Now how will draw the graph? So from this to this point MF will increase. After that MF is decrease. If I will ask what is the critical value of R at zeta equal to 0.1? This. Why it is critical? Because at this R MF is maximum. Okay. Similarly, suppose I am drawing the graph for zeta equal to 0.2. Now this thing will fit in your mind. So the value of R at which MF is maximum will move more towards left side of R equal to 1. Yes. Now the value of MM max further it will reduce further. So suppose I am getting MM max here. It will be less than this, but it will be greater than this, greater than 1. So what will happen? From this to this, MF will increase. After that, MF will decrease. So this is the graph for zeta equal to 0.2. Like this, you can draw the graph. Okay, and like this, it will reach to zeta equal to exactly 1 by root 2 now. So at zeta equal to 1 by root 2, MF will be maximum at r equal to 0. And at r equal to 0, value is 1. So value of MMX will be 1 and it will, after that, it will continuously reduce. So it is the graph for zeta is equal to 1 by root. It is the graph for zeta equal to 1 by root. Clear? Yes. Now what about zeta greater than 1 by root 2? In greater than, is here you can include equal to 1 by root 2 also. So see, what was the pattern for zeta equal to 1 by root 2? For zeta equal to 1 by root 2, MF is maximum at r equal to 0. And after that, continuously MF is decreasing. So same will be pattern for zeta greater than 1 by root 2 also. Because now we cannot go beyond this side, na? Because frequency ratio will always be positive. So for zeta greater than 1 upon root 2 also, na, MF will be maximum at r equal to 0. And we know at r equal to 0, MF is 1. So maximum value of MF will be 1. Means suppose if you are drawing the graph for zeta 0.9, 0.9 is greater than 1 by root 2. So for that value of zeta also, MF will be maximum here and maximum value of MF will be 1. And after that, it will continuously reduce. But what will happen? After zeta equal to 1 by root 2, if you are increasing the zeta, graph will shift more towards downward side. But pattern will be same. Pattern will be same means MF is maximum is here, maximum value of MF is 1. And after that, MF is continuously decreasing. Okay. So here, more important point to understand in this graph is the pattern of the graph between 0 to 1 by root 2. After that, all discussion is easy. Okay, so I think this graph is clear. Now I am making the summary. Only you have to remember the summary, na? Yes. First of all, summary related to magnification factor. First of all, general equation to calculate MF is 1 upon square root of 1 minus r square whole square plus 2 zeta r whole square. Now remember one more point. Sometime examiner will ask calculate magnification factor at resonance. So see, resonance r equal to 1. R equal to 1 means when forcing frequency, that is omega, or frequency of steady state vibration, which is also omega, is equal to natural frequency, that condition is known as resonance. So whenever examiner is asking anything at resonance, so remember resonance is nothing but resonance means r equal to 1 condition. Okay. So this you can remember. Now resonance means r equal to 1. Okay. Now if you will draw the graph, I am making the final summary for zeta equal to 0. See. So for zeta equal to 0, equation of MF will be like this: square root of 1 minus root over 1 minus r square whole square. This you need not to remember. Here if you put zeta equal to 0, automatically you will get this equation. But important point is, for zeta equal to 0, MF is maximum. This you can see at in graph also, at r equal to 1, and maximum value of MF is infinite. So can I say it is worst condition? Because MF is infinite, system will get collapse. So it is critical condition. Means if examiner is asking now, can I say for no damping, critical condition is resonance, or MF will be maximum at resonance, because R equal to 1 is resonance. Okay. But this is for zeta equal to 0. Now what about for zeta greater than 0, less than 1 by root 2? For numerical, can I say in this range MF is maximum at R equal to root over 1 minus 2 zeta square, and the formula to calculate maximum value of MF, examiner asking calculate maximum of MF, the formula is 1 upon 2 zeta root over 1 minus zeta square. Okay, if you want you can remember this equation. Okay, 1 upon 2 zeta, but this equation is only valid for this range. Okay. Okay. Yes. Now with respect to graph, what are the important point? Between 0 to 1 by root 2, the value of R at which MF is maximum, if you are increasing the zeta, this value of R or this point will shift more towards left side of R equal to 1. And the maximum value of MF will reduce. Max value of MF will reduce means whatever max value of MF you are getting zeta equal to 0. Now max value of MF for zeta equal to 0.1 will be less than that. Okay. So from 0 to 1 by root 2, if you are increasing the zeta, the value of R at which MF is maximum shift towards the left side of R equal to 1, and the value of MM max will reduce. This is, you can see it is visible in the graph. So you need not to write that as a point. From graph you can conclude. Even if you want to write, I am writing. Okay. Between zeta equal to 0 to 1 by root 2, by increasing zeta, I am writing in short, the point means the value of R at which MF is maximum shifts towards left side of R equal to 1, and value of MF max reduces. Okay. Sometime examiner will ask at for zeta equal to 0.1, what is the critical value of R? So critical value of R means at which MF is maximum. So this is the critical value of R. Sometimes examiner can ask theoretical question like this: if system is slightly damped means zeta is not 0, but it is very less, say 0.1, 0.05. So at which value of R is critical, or at which value of R MF will be maximum? It will be at resonance, or left side of resonance, or right side of resonance. So see, just assume in your mind zeta is 0.1. So for zeta equal to 0.1, MF will be maximum at this R, which will be less than 1, means lesser than resonance, and that point will be in the left side of resonance. Na? So for slightly damped system, you will get critical value, or you will get the R at which MF is maximum at left side of resonance, because it is lesser than 1. Na? Yes. Now, what about the point related to graph for zeta greater than equal to 1 by root 2? For this case, simply you can remember MF is maximum at R equal to 0, and maximum value of MF is 1. Because at R equal to 0, MF is 1. After that, it is continuously decreasing. So don't be in a hurry. Sometimes examiner asks what is the maximum value of MF, only to see your concept. For zeta equal to 0.1. So what is student do now? They put zeta equal to 0.9 here and they get maximum value of MF. But that is incorrect. Because zeta equal to 0.9 is greater than 1 upon root 2, so this equation are not valid. For greater than 1 upon root 2, MF is max and R equal to 0, and maximum value of MF is, sorry, not 1, na? Sorry, it is 1. So answer will be 1. Okay. So see the question carefully. Okay. So these are the important part related to the graph of MF. Okay. And some general question is coming in which exam asking value of MF and NAR at any zeta, just put here. But exam asking at which RMF is maximum, what is the max value of MF? So that discussion I had done. Clear? Okay. Like we are solving the sum question. Solve this question. I'm just bringing the calculator. Now wait for 1 second. See. See what this question is saying. For damping factor means for damping zeta equal to 0.2, the magnification factor is maximum at frequency ratio, means at which value of our MF is maximum, that examiner asking. Okay. And what is the maximum value of MF? Okay. But this calculation we have to done for zeta equal to 0.2. Now see, zeta equal to 0.2 is less than 1 by root 2 or it is greater than 1 by root 2. So see, 1 by root 2 is 0.707. So can I say this zeta equal to 0.2 is less than 1 by root 2? Yes. So these equations are valid. If zeta is between 0 to 1 by root 2, can I say that MF is maximum at R equal to root over 1 minus 2 zeta square? So just do the calculation. Root over 1 minus 2 zeta square. And zeta is 0.2, so 0.2 square. How much it is coming? Root over 1 minus 2 into 0.2 square, you can check. It is coming 0.959. So at this value of our MF will be maximum, na? 0.959. Okay. Second, what is the maximum value of MF? That you can calculate in two ways. In the equation of MF, put zeta equal to 0.2 and R equal to this, because at this our MF is maximum, you will get maximum value of MF. But we know direct equation to calculate maximum value of MF. Since zeta is less than 1 by root 2, so you can use this direct equation. The formula to calculate maximum value of MF for any zeta is 1 upon 2 zeta upon root over 1 minus zeta square. So just put the value of zeta here. So how much maximum value of MF is coming, and whatever this value will come, it will be less than infinite, but it will be greater than 1. Automatically it will come. 2 zeta is 0.2 root over 1 minus 0.2 square. How much it is coming? $2.552. So this is the maximum value of MF. Okay. Similarly, next question. For damping factor 0.9, the maximum value of MF at R equal to and maximum value of MF is. So see, here na, zeta equal to 0.9 is given, and you can see this is greater than 1 by root 2, because 1 by root 2 is 0.707. And if zeta is greater than 1 by root 2, we know MF will always be max at R equal to 0, and maximum value of MF is 1. No calculation is required. That's it. So this is the answer for this question. Okay. Now next question. These are the simple questions. What this question is saying, a spring mass system with mass of 10 kg. So mass of the system is 10 kg. Spring constant means stiffness of the spring. It is 1600 Newton per meter. Is subjected to harmonic force. So it is external force 100 sin omega t. So what is the amplitude of this force? 100. F naught is 100. What is forcing frequency? It is omega, but omega is not given. Then examiner asking resonance will occur at omega equal to. So examiner asking the condition is resonance. So examiner asking forcing frequency at resonance. And we know resonance means R equal to 1. So here now just remember resonance means R equal to 1 and R equal to 1 means R is omega by omega n. Means can I say at resonance omega is equal to omega n. So here indirectly examiner is asking natural frequency because examiner is asking forcing frequency. But we know for resonance forcing frequency is equal to natural frequency. And for natural frequency we know direct formula. For general case formula is root k by m. For other case it is root ke by ma. But if diagram is not given, always consider general case. So it is root k by m. So here you have to only calculate omega n, and here omega is equal to omega n because examiner is asking at resonance. Now root k by m. K is 1600. Use SI unit na, Newton per meter, upon m is 10 kg. So how much it is coming? Root over 1600 divided by 10. It is coming 12.649 radian per second. Now at resonance we know omega is equal to omega n. So this forcing frequency is also 12.649 radian per second. So this is the answer for this question. Resonance will occur at omega equal to 12.649. Clear? Okay. Now these questions simply in force vibration formula based question will come. A single degree of freedom spring mass system with viscous damping has a spring constant of 10 kilonewton per meter. So K is given, it is 10 kilonewton per meter. Convert in SI unit. 1 kilonewton is 1000 newton, so it will be 10,000 newton per meter. The system is excited by sinusoidal force of amplitude 100 newton. So harmonic force is acting and amplitude of that harmonic force is given, means F0 is given. It is 100 newton. Now if the damping factor or damping ratio is 0.25, so zeta is given directly, it is 0.25. The amplitude of steady state vibration at resonance. Amplitude of steady state vibration means examiner is asking steady state amplitude, that is capital X. But examiner asking this steady state amplitude at resonance, or resonance means value of R is given, it is equal to 1. Because examiner asking at resonance. Resonance means simply R equal to 1. Now see, we had to calculate capital X at resonance. And what is the formula to calculate capital X? It is F0 by K upon root over 1 minus R square whole square plus 2 zeta R whole square. Now for capital X calculation we required R is given, it is 1. We require zeta is directly given. We require F0 is 100 newton. We require K is 10,000 newton per meter. So put it. But if you are putting in SI unit, it will come in meter. But examiner asking in mm na. See, in meter it will come very lesser value. So I will suggest calculate this in the order of 10 to the power minus 3 minus 4. After that, to convert this in mm, we will multiply with 1000. You will get capital X in mm. So calculate in 10 to minus 3 order na, at least, to ensure accuracy. F0 is 100 divided by K is 10,000. Resonance means R equal to 1 na. So you will put R equal to 1 here. It will be 1 minus 1, 0, 0 square means 0, plus 2 zeta. Zeta is 0.25. R is 1 na. It will be 100 upon 10,000. Now it is 2 into 0.25 whole square because this part is 0. So you'll bring outside root, it will be 2 into 0.25. Okay. So how much it is coming? 100 upon 10,000 into 2 into 0.25. It is coming 20 into 10 to the minus 3 meter. You can check the calculation. Okay. Now examiner is asking in mm, so it will be 20 mm. So for this question, the value of steady state amplitude is coming 20. Clear? So this is the answer for this question. Now next, this question. What this question is saying? Just read the question. A single degree of spring mass system is subjected to sinusoidal force of 10 Newton amplitude. So it is the amplitude of force, means F0 is given, it is 10 Newton. Frequency omega along the axis of a spring is, means it is the frequency of force, means forcing frequency is given. Okay. It is denoted as omega, and we are already denoting forcing frequency as omega. So it is forcing frequency, na? Omega is forcing frequency. Okay. Now the stiffness of the spring is 150 Newton per meter. K is given. And damping factor is 0.2, zeta is given. Undamped natural frequency is 10 omega. Means omega n is given. Omega n is 10 omega. It is given in terms of omega. So now I can calculate frequency ratio also, na? Because we know frequency ratio R is omega by omega n, and omega is forcing frequency, which is already omega, and omega n is natural undamped frequency, which is 10 omega. So indirectly for frequency ratio R is given. It is omega divided by 10 omega. So it is coming 0.1. So the value of R is given. So here both R and zeta is given indirectly. Okay. So at steady state amplitude of vibration in meter approximately, it will come very lesser, na? So calculate in either 10 to minus 3 minus 4 order, or at least calculate up to 2 to 3 decimal place, because the examiner is asking up to 2 decimal place. So we have to calculate steady state amplitude, capital X. Now we know what is the formula to calculate steady state amplitude. Again, it is simply formula based question. F naught by K upon root over 1 minus R square whole square plus 2 zeta R whole square. Now R is given, it is 0.1, zeta is given 0.2, F naught is given 10 Newton, and K is given 150 Newton per meter. So put all value in meter. Sorry, in SI unit. You will get capital X in meter. 10 divided by K 150 upon root over 1 minus R square. R is 0.1 whole square, then whole square plus 2 zeta. Zeta is 0.2 into R is 0.1, it's whole square. Now do the calculation. 10 divided by 150. First I am calculating this part. Root of 1 minus 0.1 square whole square plus 2.2.1 square. It is coming 0.991. At least do calculation up to 3 places. It is coming 0.067 meter. Means around, if you round up to 2 decimal place, because examiner is asking up to 2 decimal place, it is 0.07 meter. So capital X is 0.07 meter. Examiner asking in meter, matching with which option? Option B. So for this question, option B is correct. Clear? Like this. This is last question. One more question I am discussing. It is an 80 question. What this question is saying? A spring mass desktop system has a mass 10 kg, M is given. Spring constant K 6250 Newton per meter is excited by harmonic force 10 cos 25 T Newton. So the amplitude of this force means F naught is 10 Newton and forcing frequency, that is omega. Inside cos, see the coefficient of time, it is 25. So forcing frequency is 25 radian per second, which we are denoting as omega. Now at steady state the vibration amplitude is 40 mm. So can I say here steady state amplitude, that is capital X is given, it is 40 mm or 40 into 10 minus 3 meter. Then examiner asking damping coefficient of the damper, C. So for this, first we'll calculate zeta. After calculating zeta, we can calculate C also. So see, here capital X is given now. And now what is the formula to calculate capital X? It is F naught by K upon root over 1 minus R square whole square plus 2 zeta R whole square. Now here our capital X is given. So from this capital X we'll find zeta, because now C is unknown means zeta is unknown. So first we'll calculate zeta, then from the equation of zeta we can calculate C. So here our objective is to calculate zeta. But to calculate zeta we should know capital X, it is given. We should know F naught is also given 10 Newton. We should know K is also given 6250 Newton per meter. We should know R is omega by omega n. So now first we'll calculate R na. Okay. So R is omega by omega n. Omega is known 25 radian per second. Now what is omega n? omega n is natural undamped frequency, it will be root over k by m. Now root over k is 6250 Newton per meter and m is 10 kg. So omega n is coming root over 6250 divided by 10, 25 radian per second. So R is omega by omega n. Omega is also 25, omega n is also 25. So R is 1. Means it is resonance case. It is not written directly that is resonance, but ultimately R is coming 1 means it is resonance case. Okay. So calculation will become simpler. But whatever R is coming, whether it is coming 1, 0.8, 0.9, we have to put here. Right now R is coming 1. Okay. So now just solve the. Okay. Now first I am simplifying this equation by putting R equal to 1 because this equation will become simpler. Like F naught by K. Here we will put R equal to 1. This part will be 0 plus it will be 2 zeta whole square. Now I will bring 2 zeta whole square outside root. Can I say it will become 2 zeta? So what we have done, we have put it R equal to 0 first. R equal to 1 first. Now I am putting other value. Capital X is 40 into 10 minus 3 meter. I am using SI unit. Equal to F naught is 10 Newton divided by K. K is 6250 into 2 into zeta. So in this equation only one unknown zeta is coming. So we can calculate zeta. How much it is coming? 10 divided by 6250 into 2. This part will come below side. Zeta is coming 0.02. You can check. Yes. Now we have calculated zeta. Now what is the formula to calculate zeta? It is C upon 2 root over Km. From this we can calculate C also. Zeta is 0.02. That is equal to C upon 2 root over Km. K is 6250 into M. The value of mass is 10 kg. So from this we can calculate the C, which is damping coefficient of the damper. It is coming 0.02 into 2 into root 6250 into 10. It is coming 10. Yes. Newton second per meter. So in Newton second per meter, the damping coefficient of the damper is coming 10. Exam asking Newton second per meter. So for this question, the correct answer is 10. Okay, so this is all about force vibration. Okay, so today we have discussed the introduction of force vibration. Then in force vibration, we have discussed the force vibration, or you can say force damped vibration for a spring mass system when it is subjected to harmonic force. Okay, and during this discussion we have discussed one more important concept, that is the concept of magnification factor. So it is completed. In force vibration one more concept comes. This is the concept of vibration isolation. But this vibration isolation I have already discussed separately in this YouTube channel. If you in GATE Wallah English YouTube channel, if you search vibration isolation, you will get complete lecture related to vibration isolation. So if you want, you can watch that lecture. Okay. So that's all for today. Today we have discussed the force damped vibration of single degree of freedom system. Okay. So I'm ending the class now.